Alright, in this video we are talking about random variables. We're starting chapter 5, and there's actually two kinds of random variables we need to talk about. Alright, the two types of random variables. So suppose that you toss a fair coin 3 times. The sample space for this process is, you tossed it 3 times and you get 3 heads. So here's the first toss, second toss, third toss. Then if you toss it again, you could get heads, heads, tails, heads, tails, heads, tails, heads, 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 tails, 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 heads, tails, 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 heads, tails, tails, tails. So there's all different ways those 3 coin tosses could come out, different outcomes basically. So because there are 8 equally likely outcomes, the probability is 1 out of 8 for each possible outcome. Now, the reason we got 1 out of 8 is because to toss a head, it's 1 out of 2, right? To toss a head again is 1 out of 2, and then the third one is 1 out of 2. And you multiply all those 3 together and you get 1 out of 8. And those 3 probabilities stand true whether it's heads or tails because they're equally likely. Now, define the random variable x as the number of heads obtained in 3 tosses. The value of x will vary from one set of tosses to another, but it will always be one of the numbers 0, 1, 2, or 3 because you have 0 heads, 1 head, 2 heads, or 3 heads in your outcome. So how likely is x to take on each of these values? So we look at our sample space up here. Well, how many times did x equal 0? No heads. Well, only one outcome where it was tails, tails, tails. So from that we get 1 out of 8. Well, how likely is it that I get 1 head? Well, here's one outcome that comes out with 1 head. Here's 1, here's 1. And there's 3. So 3 out of 8. How likely is it to get 2 heads? Well, there were 3 outcomes in the sample space again, so that makes 3 out of 8. And then how likely to get 3 heads? Well, that only happened 1 time in our 8 outcomes, so that was 1 out of 8. So we summarize the probability distribution of x in the table. And notice the top is all the possible outcomes, and the bottom is the probability of each outcome. A random variable takes numerical values that describe the outcome of a chance process. The probability of a random variable gives its possible values and their distribution and their probabilities. Probability distribution of a random variable gives its possible values and their probabilities. So this was the bottom row. Okay, random variable takes numerical values that describes the outcomes. This was the top row in the table. There are 2 types of probability distributions corresponding to 2 types of random variables. One is a discrete random variable and one is a continuous random variable. So a discrete random variable takes a fixed set of values with gaps between them. The probability distribution of a discrete random variable lists the values x and their probabilities. Okay, so don't let these little subscripts and stuff weird you out. This is just saying the value of 0 heads, 1 head, 2 head, 3 heads, and then the probabilities that go with them. Now, in a valid probability distribution, the probabilities, all of this bottom row, must satisfy 2 requirements. Every probability is a number between 0 and 1 inclusive, meaning it could be 0 and it could be 1, but it's not going to be greater than 1. So notice between 0 and 1 there's a lot of decimals. So you're going to have fractions, less than 1 decimal. The other requirement is that the sum of all these probabilities have to add up to 1. All right? So you can use the probability distribution of a discrete random variable to find the probability of an event. So back to our number of heads and coin tosses. Here was our table when we tossed it 3 times. All right. So here's a question. What's the probability that we get at least 1 head in 3 tosses? Well, at least 1 head. Well, here's 1 head, here's 2 heads, and here's 3 heads, right? So at least 1 head means I would add up each of these 3. Okay? And that's what I have right here. 1/8 is the 3 heads, 3/8 is 2 heads, 3/8 is 1 head. You add them all up and you get 7/8. Now, you could also use the complement rule, which means, remember we talked about how all of these, back in chapter 4, all of them add up to 1. So if I want everything except this one piece right here, I could do 1 minus this little piece and it would come out the same. So in symbols, it looks like this. The probability that x is greater than or equal to 1 is equal to the probability that x is less than 1, because it's either greater than or equal to or less than, right? So if I can find this value right here on the table, which I can, and I just subtract it from 1, I get my answer. So either way is correct. Either way you want to look at it is correct. Now, what we just did was discrete random variable, okay? Number of heads was either 1, 2, 0, 1, 2, or 3. There was no 0.5 heads, 1.5 heads, anything in between those two. Those are discrete little packages of numbers, 0, 1, 2, 3. Just like the number of your siblings. You have 0, 1, 2, 3, 4, whatever. Or a number of my students. They're discrete numbers. There's no decimals in between them, okay? Now, that is a discrete number, but what about a continuous number? So if you want to randomly select a number between 0 and 1, allowing any number as the outcome, like this giant decimal or this giant decimal, we have a whole lot more possibilities, if you will. The sample space of this chance process in the entire interval between 0 and 1 on a number line, okay? If this is the scenario we're going for. If we determine y is the outcome of a random number generator, then y is a continuous random variable. It can take any value in an interval on the number line. That includes decimals, okay? Decimals included. Most discrete random variables result from counting something, like counting students, counting puppies, counting sheep, whatever. You're counting. They're whole numbered things. Continuous random variables usually result from measuring volume, measuring weight. Those are things that we have decimals with, okay? Fake numbers on tax returns, invoices, or expense account claims often display patterns that aren't present in legitimate records. Some patterns, like too many round numbers, are obvious and easily avoided by clever crooks. Others are more subtle. It's a striking fact that the first digits of the numbers in legitimate records often follow a model called Benford. Call the first digit of a randomly chosen record X for short. Benford's law gives us the probability model X that the first digit can't be a 0. Show that this is a valid probability distribution. So they're saying, okay, the first digit on any expense in this expense report, probably the first digit's a 1 is 0.301. Probability that the first digit's a 2 is this, 3 is this, 4 is this, 5 is this, so on and so forth, okay? And that the first digit can't be a 0, all right? So the question is, show that this is a valid probability distribution. So this goes back to the two requirements. The first one is that all the probabilities, the second row here, have to be less than 0. And you can look at those and see, okay, they're all not less than 0, I'm sorry. They are all less than 1. They're between 0 and 1. So the first requirement was that all probabilities have to be between 0 and 1. And if you look at all of these, they're between 0 and 1. They're all decimals. So we meet that qualification. The second criteria was that all the probabilities have to add up to equal 1. So if you put all of those probabilities in the calculator and you add them up, you get a 1. So by proving those two things, I can prove that this is a valid probability distribution. Now, from the previous example, it says describe the event X is greater than or equal to 6 in words. You have to think about, okay, what does this 6 mean? Greater than or equal to 6 could be any of these values, right? The event X is greater than or equal to 6 is the event that the first digit of a randomly chosen legitimate record, that's context, right, is greater than or equal to 6. So context, here it is again. You have to include context in your answers for it to be correct. Okay? You got to be able to read that this is greater than or equal to. Then the next part of this says, okay, then what is that probability that X is greater than or equal to 6? So I look in my table. What are those probabilities? And I add them up. Okay, and that's what I've done here. And I get 0.22. Easy enough. All right, then the last type of question you're going to see in your homework is being able to classify a discrete random variable and a continuous random variable. Okay, remember discrete? How do you remember this? Well, this is more of a counting thing. And continuous kind of goes towards measurement, okay? And you can have decimals with continuous, okay? Counting, no decimals. So let's look through this, okay? If X is the pH of a water sample that has been randomly selected from a stream. Well, pH is a measurement of acidity, so it's a measurement, so that would make that a continuous random variable. All right, on B, if Y is the number of correct answers on a multiple choice test for a randomly selected student in your class. Okay, correct answers, is black and white. There's not like 2.3 correct answers. It's pretty, you got 10 out of 15 or 20 out of 30. Those are clear counted answers. There's no decimals there. So that would make that a discrete random variable. If W is the exact amount of sleep that a randomly selected student from your school got last night. If it's exact, that's a measurement. Okay? We tend to round it to hours, but if it's exact, that could be, 5.23 hours. It's not exactly 5 hours. So that's more likely a continuous random variable. All right, so you're going to be asked to do questions like this on your homework. We'll do some more examples in class.